We are going to finish up our lecture on properties of gases. So what we're going to talk about next is Henry's law and some on solubility coefficients. Alright, so solubility coefficients. It's important to remember that gas can be dissolved in a liquid. And it's actually Henry's law that predicts how much of a given gas will be able to dissolve in a liquid at any given temperature. And so it is variable depending on the temperature. But basically what this equation shows here is V is for volume is equal to whatever that solubility coefficient is of that particular gas, because gases are going to vary, times the partial pressure of that gas in a mixture of gases. Here's a YouTube video that I'll post for you to watch. And so what do you know about gases dissolving in a liquid? Well, you've all drank a bottle or can of soda, and if we think about a soda can, that is CO2 dissolved in a liquid. And whose law talks about that? Well, again, that's Henry's law. And if you think how we can change that amount of fizz in a soda, if you notice, if you've opened a soda, if you have an open bottle of soda, and you put it in the fridge, a lot of people will do that after they've opened a soda, put it in the fridge, because it'll still fizz if it's in the fridge, in part because there's less movement of those gases at a lower temperature, and some of that fizz stays in. If we have it at room temperature, at a warmer temperature, there's more movement to that gas, and the more of the carbon dioxide is going to escape out of the soda bottle. And then we've all done this, where you shake up a soda and you agitate a soda. As you're agitating it or shaking it, you're increasing its kinetic energy, so increasing that speed that that gas is moving through there, and it pops open. So for solubility coefficients, they are different depending for different gases. We will look at all of these at STPD, or standard temperature pressure dry. And what we see here is that if we look at the solubility coefficient of oxygen in the plasma at 37 degrees, so 37 degrees Celsius is normal body temperature. So when we're doing these calculations, that's primarily where we start. 760 torr, again, is sea level, where most textbooks use to write these equations, and that does reflect a standard measurement, which is, so for oxygen it's 0.023 mils of oxygen will be able to dissolve in each milliliter of plasma. Under the same conditions, then that same temperature and same pressure, 0.51 mils of CO2 can dissolve in that same milliliter of plasma. So which gas is more soluble? Well, the more soluble gas is CO2. So when we think about carrying the oxygen in the blood, we really have to discuss two components. We know blood is carried in two ways. It's either dissolved in the plasma or bound to hemoglobin. And that dissolved portion is really, really small, and oftentimes we sort of disregard it, because if we look at the amount of oxygen that can dissolve in 100 mils of blood, it just winds up being pretty minimal. But it is that partial pressure of oxygen, so whatever that value is that we would get from a blood gas, we would take that value, the partial pressure of oxygen, times 0.003 mils of O2 per 100 mils of blood. and that 0.003 value is derived from the mathematical manipulation of the solubility coefficient. So we don't necessarily have to know how that is done, but that's where we get it. So here it is. It's 0.023 mils of oxygen in 1 milliliter of plasma divided by 760 times that 100. See what you get when you calculate out that calculation. Okay, so now let's talk about Fick's law of diffusion. Really what Fick's law says is how gas moves through through membranes is related to this calculation. So really what it is you'll find it in your text, but it's the flow of gas is related to the area, the surface area that's available, the thickness of the alveolar wall or alveolar membrane, whatever we're looking at, but the thickness of the substance that it's passing through. And if you look at that P1O2, and then you see that red line that reflects over to P2O2, that's the pressure difference between these two areas. So again, when we think about diffusion, it's movement from areas of high concentrations to low concentrations. So the greater the difference in partial pressures, the more driving pressure there is to move that gas across that membrane. So if you think about as area increases or as pressure increases, we'll get more diffusion. On the flip side of that, the thicker the membrane, the slower the diffusion. So, what do these values equal? And which piece of this is Graham's law? Well, remember, Graham's law comes back to that square root of the gram molecular weight. And Henry's law goes back to, Henry's law talks about the pressure differences of the solubility coefficients. So Fick's law really brings a lot of these together. So if you think about it, in the lung, convection accounts for gas movement to about the terminal bronchial level. The diffusion is primarily mechanical. The diffusion is the primary mechanism, I should say, for gas movement to the lung parenchyma. Since temperature, pressure, distance, and molecular weight of a gas are constant during normal breathing. The factor most affecting diffusion in the lung is cross-sectional area. Things like secretions, bronchoconstriction, mucosal edema all decrease the cross-sectional area, therefore slowing diffusion. In order for gas to diffuse across the alveolar capillary membrane, it must first dissolve into a liquid, the plasma. Henry's law defines those factors that account for that solubility. It states that the amount of gas that can dissolve in a liquid is directly related to the partial pressure of the gas and indirectly related to the temperature in the system. In addition, the amount of gas that can dissolve in a liquid is dependent on the chemical structure of the gas. That relates back to that solubility coefficient. Once dissolved, gases must diffuse through the liquid. Graham's law states that the rate of diffusion of a gas through a liquid is indirectly related to the square root of the gram molecular weight of the gas. So if we think about looking at the solubility coefficient differences of CO2 and oxygen, which one has a much higher solubility coefficient? Well, that would be the CO2. CO2 is generally about 19 times more soluble than oxygen. However, what balances this out in the diffusion is that oxygen has a larger pressure gradient than does CO2. If you have any questions, we can talk about those in class. Please refer to your book for other readings on this material.